Trapping electrons in certain dimensions. To give you a brief example, suppose we have a solid, it's a bulk material, and then we take a slice of this solid material. We take a slice of the solid material and form a thin sheet. So in the bulk material, if we have a free electron, the free electron is constrained to move in 3 dimensions. It can move along x, y or z. But if we reduce the thickness of this material so that we have a sheet, we have a sheet of 0 thickness, then we are constraining the electron to move only in 2 dimensions. So we are getting a low dimensional material. This is a higher dimensional material and this is a lower dimensional material. We can constrain the electron to move in even a smaller dimension, that is 1 dimension. By reducing the width of this sheet, we can form what is called a wire. So this is a 1-dimensional material. We can even reduce the dimensionality of this material further so that the electron is trapped on an island. So we have a small island on which the electron is trapped. In such a case, the electron is in a 0-dimensional material. It's in a point-like environment. So this is a solid. It's called a quantum well or a quantum sheet. This structure is called a quantum wire. And this is called a quantum dot. So as we are going from top to bottom, we are reducing the dimensionality of the system and we are localizing the electron further and further and further. In other words, we are constraining the electron to move in a smaller number of directions. And as a result, the energy levels of these structures gets discretized. For example, for a quantum dot is very similar to an infinite well. If on this axis we have the energy, and if on this axis we have another object that is called the density of states, which we will study in detail after the midterm, then we know that for an infinite well or for a quantum dot, only precise energy levels are possible. So only precise values of energies are possible inside this 0-dimensional structure. This is what a quantum dot is. On the other extreme, we have a solid. In a solid, the density of states versus the energy is a continuous spectrum. And this is called a band. And it's not discrete. There are finely spaced levels and they are so close together that in effect you have a band, a continuous distribution of energy levels. These are the two extremes. This is a bulk material, whereas this is a constrained material. On the other day, we made the statement that localization leads to quantization. So we have a localized structure here. An electron is confined to move in a 0-dimensional material, in a quantum dot. And these quantum dots can be made. They are made in the laboratory. And they are just like artificial atoms. This is what the energy level of an atom will also look like. So if you constrain the dimensionality in a quantum well or a quantum sheet, you will have some kind of discretization. if you plot the density of states, it will have a staircase pattern. And if you talk about a quantum wire, for a quantum wire, the density of states versus the energy will look something like this. So you are localizing the electron as you go from top to bottom. You just reducing the dimensionality of the system. These are low dimensional systems. This is a two-dimensional system, a one-dimensional system, a zero-dimensional system. And as you are confining the electron to fewer and fewer dimensions, you get discretization and quantization. And this is what we observed the other day when we were talking about an infinite well. There was a question here.
Sir, how would we interpret the electron is moving in a zero dimension in a quantum world? In a wire we say it moves in an x direction. So how is an electron moving without any dimension?
Okay, so this fine student has asked a question and he's used the term moving of an electron. How does an electron move? Now the moving of an electron is not a very legitimate question to ask in quantum mechanics. Let me give you an example. In fact, your question leads me very smoothly into what I wanted to discuss now. That is, how does an electron get across nodes in an infinite well? We'll talk about this after the midterm, but all of you know what a p orbital looks like. You've studied it in freshman chemistry. A p orbital is a dumbbell structure. Looks like this. This is pz, this is px, and this is py. If this is x, y, z. So these are our p orbitals. But what are these p orbitals really? These p orbitals are pictures of the probability density squared, of the probability density. So these p orbitals are actually pictures of psi. Since we're talking about 3 dimensions, let's talk about the position vector instead of x, modulus squared. So these p orbitals are photographs of the probability density for certain energy levels inside a hydrogen atom. Now this point is a node. This point is a node. Likewise, this point is a node. And there is zero probability of finding the electron at the node. If there is zero probability, then how can an electron move from one lobe of the p orbital to the next? That should not be possible. In the Greek period, there was a philosopher with the name of Zeno. Now Zeno talked about, he talked about something very interesting, which is called the Zeno's paradox. Suppose you throw an arrow. It was a hunter-gatherer community. You throw an arrow, and you take photographs of the arrow. I'm now casting his argument in modern terms. You take photographs of the arrow with a camera that has infinite shutter speed. Now those photographs, each one of them will be a still image of the arrow, and the arrow will appear to be at rest inside each frame, inside each photograph. So if an electron is photographed in a p orbital and you consider this to be moving from this lobe p1 to p2, then at certain instances, if you have an infinite speed camera, you should be able to detect the electron at the position of the node. But that's not possible according to quantum mechanics, because the Schrodinger equation is solved and it gives you a zero wave function at the node. A zero wave function means a zero probability density. How does the electron then get across the nodes? The only way in which we can explain this paradox is by stating that we should forget thinking about the electron as being a particle in motion. This is an image of the electron at any one instant. This picture tells you the field of the electron, and it exists everywhere. This is the wave function, or the wave function squared of the electron, and if you were able to take an image of the wave function itself, which is not possible, if you were to take an image of the field, if you were to take an image of the quantum field or the wave function or the matter wave, it will look like this. But the problem with us mortal classical human beings is that we cannot image the field, we cannot image the wave function. What we can image is the collapse of the wave function. That is, the wave function collapses onto certain discrete points. So if you want to measure the electron, this wave function will collapse, and you will get a point somewhere in this lobe, or a point somewhere in this lobe, or another point in this lobe, or another point in this lobe. And if you repeat the experiment a large number of times, your points will have a density, they will be distributed in accordance with this wave function squared. And you will never be able to find an electron at the node. So the act of measurement collapses this field, and if you perform the experiment on identical copies of the electron, many electrons that exist in the py orbital again and again, not the same electron but identical copies of the electrons, then you will get a distribution, a discrete distribution, which will resemble this p orbital. But we should stop thinking of the electron as being as a particle that is in motion, because then you will have to explain why doesn't the electron exist at the node. So this is a picture of the field, a picture of the wave function, which of course as mortal human beings we cannot image. What we can do at best is to collapse this wave function and find the individual positions of the electrons. And when we repeat the procedure a large number of times, we reproduce this probability distribution.
Sir, if the probability of finding an electron at the node is 0, then shouldn't the probability of any wave being at that node equal to 0?
It is 0. The wave function is 0 here. It is 0. और ये क्या है? ये दरअसल न्यूक्लियस है. वेव फंक्शन 0 है इस पॉइंट पर.
So then you said if we consider electron as a wave, then it...
Yes, that is why I would like to say that the electron, quantum mechanics talks about potentialities. पोटेंशियल एनर्जी का मतलब किसी ऑब्जेक्ट में एनर्जी जो उसके अंदर छुपी हुई है, अब वो किसी तरह उसको आश्कार होना है, काइनेटिक एनर्जी की सूरत में, हीट की सूरत में. क्वांटम मैकेनिक्स टॉक्स अबाउट पोटेंशियलिटीज. दिस इज, इफ यू ड्रॉ दिस wave function, the wave function will be the under root of this, so it will resemble this. If you draw the wave function, this gives you the potentiality of locating the electron at certain points. It talks about potentiality. So quantum mechanics is about potentialities. Alright, so this is how this is how we explain the paradox that how does an electron get across nodes, and this was a question that I asked when I was talking about the infinite well. Now suppose we relax the condition of the infinite well and instead let's have a well which has not an infinite height, an infinite potential energy, which of course is hypothetical and just a figment in our imagination. Rather, let's talk about a more realistic scenario in which the height of the barrier is not infinite, it's finite. Suppose our well is like this. So this, we're talking about one dimension, so x is 0 here, x is L here. The potential energy in the well is 0, and this potential energy is not infinite but U naught. The The first question, the first case. Suppose an electron has an energy which lies here, and it's E. This is the energy of the electron. So it's above the barrier. Classically, what do we expect? First question, is the electron bound? तो सबसे आखिर में बैठे हुए साहब बताएं, इलेक्ट्रॉन बाउंड है यहां पर जी? इट विल बी बाउंड? नो, इट्स नॉट बाउंड. बिल्कुल ठीक. The electron is not bound. It will have kinetic energies. It will have a small kinetic energy here, and it will have a large kinetic energy in this region. So how do we solve the Schrodinger equation for such a system? And what will the wave function look like? Okay, let's write down the Schrodinger equation. Minus h bar square 2m psi. I'm dropping the x, assuming that the x always exists, the argument, plus the potential energy x psi equals Ex, E psi. Now E is constant, and this means that minus h bar square 2m psi equals E minus U psi G. Sorry. Now this is the most general form of the time independent Schrodinger equation. We have three regions. Region number 1, region number 2, and region number 3. How are these regions different? When x is less than 0, u is u naught. When x is greater than 0 and less than L, u is 0, and when x is greater than L, u is again u naught. So this is how we would like to solve the Schrodinger equation, and we would like to have the wave equation obey all the continuity requirements at the boundaries. So the only difference is the value of u. And if you remember from your calculus classes, u is a piecewise continuous function. ठीक है, ये लफ्ज़ सुना हुआ है ना? Piecewise continuity. U is a piecewise continuous function. So the solution to this equation, E is always greater than U. E is always greater than U. Can you write the solution of this equation? ठीक है, तो u छोटा है, e छोटा है, u छोटा है, तो u माइनस e नेगेटिव, इसको e माइनस u कर दो, फिर यहाँ आयोटा डाल दो. So if you look at the solution in region number 1, remember that E is greater than U naught. It's a very important point, do remember this. E is greater than U naught. There is an iota here. Since E is greater than U naught, this number is real. This is a real number. But since there is an iota with it, it's an exponent iota of a real number plus exponent minus iota of a real number. If U naught were equal to 0, if U naught were equal to 0 as it is in region 2, then this would be the solution. And the solution, since it's exponent iota something, it's oscillatory. This can be expressed as cosine of this times x plus some coefficient sine of this times x. It's an oscillatory function only because E is greater than U naught. In region 2, so this is region 1, in region number 2, which x is greater than 0, less than L, एक मिनट बताता हूँ, you have some other coefficients C, exponent, iota, 2me under root h bar x plus d exponent minus iota 2me, because u naught is now equal to 0. So this is the solution in region number 2. इसकी मैं complete steps आपको कर दूं एक दफा. Okay, we have this equation. We want to solve this equation. So by the general techniques that you are familiar with, we write the characteristic equation for the above differential equation. M की बजाय मैं P लिख लेता हूँ, P squared plus 2m h bar squared E minus U naught, we're talking about region 1, is equal to 0. This is the characteristic equation for the above differential equation. I have not used m here because m is reserved for the mass of the electron. So I have used P squared. So I have to find the solutions of this, the roots of this characteristic equation. The roots are P square equals minus 2m over h bar squared E minus u naught. Now remember, E is greater than u naught. So the roots will be the under root of this term, the square root of minus 1 is iota. So I get two roots plus minus iota 2m E minus u naught square root over h bar. So these are my roots of the characteristic equation. So now my solution will be, let's call these roots P1 and P2. My solution of the equation will be some coefficient A, exponent iota, or exponent P1 x plus B exponent P2x. Agreed? This is how you solve the Schrodinger equation or any differential equation which has constant coefficients. Now I put in the values of P1 and P2. A exponent P1 is this root with the positive sign, that is plus iota 2m E minus u naught over h bar x plus B exponent P2 is minus iota 2m E minus u naught h bar x. So this is the solution of the Schrodinger equation in region number 1. In region number 2, it's going to be the same solution but with u naught equal to 0. U naught equals to 0. But you will have different coefficients C and D. In region 3, it's going to be the same solution but with different coefficients E and F. And you have to find those coefficients by looking at the boundary conditions. That is, the wave function has to be continuous. But let's forget about the coefficients for a minute and see how to draw this wave function. What is the difference in the wave function between regions 1, 2 and 3? What does this wave function look like? First of all, it's a complex number. So you cannot plot a complex number. If you talk about the real part of this wave function, what will it look like? It's an oscillatory function. Cosine and sine terms are involved. You can write this function in the following form as well. A dash cosine of 2m E minus u naught h bar x plus B dash sine of 2m E minus u naught x h bar. So this wave function can also be written in this form, of course with different coefficients. So it's an oscillatory function, and it's an oscillatory function in space because we do not have any time part here. We're looking at the time independent Schrodinger equation. And what is the wavelength or the wave number of this oscillation? What is the wave number of this wave? This thing is the wave number. So the wave number in region 1 is, the square of this is equal to 2m E minus u naught over h bar squared. This is the square of the wave number. What is the wave number in region 3? It's going to be the same. What's the wave number in region 2? u naught has to be 0 in region number 2. So the wave number in region 2 is 2m e over h bar squared. This is the square of the wave number. But what is the wave number? How is it related to the wavelength? It's inversely proportional. So now if we have this situation, which I will like to redraw, which wave number is higher? This wave number is higher. This wave number is smaller. This wavelength is smaller. So the wave function, if you would like to plot the real or the imaginary part of this wave function, this is region 2, region 1, region 3. The wavelength decreases in this region. So your wave function will look something like this. This is what your wave function will look like. And it is continuous at this point and is continuous at this point. And that is how you solve for the coefficients. But the key thing is that the difference in energy and the potential energy determines the wavelength of this matter wave, of the wave function. In region number 2, you have this wave function, which is higher than the wave function in wave number in region 1 and 2, which means that this wavelength should be smaller. So I've drawn it the other way around. So this is what my wave function will look like. Is this making sense? किसने पूछा सवाल? अच्छा, देखो वेव नंबर तो फर्क है ना मुख्तलिफ रीजन्स में, and the wave number is determined by the difference in energy and the potential energy. And remember that we're talking about the case that E is greater than the potential energy. There is no region that is classically forbidden. The particle has a kinetic energy in this region, a positive kinetic energy in this region, and a positive kinetic energy in this region. So the wave function, wave numbers are different in the two regions. The wave number is inversely proportional to the wavelength. Higher the wave number, smaller the wavelength. In region 2, the wave number is higher because there's an E here. In region 1, there's an E minus U naught. So the wave number is smaller in region 1 and 3. So smaller wave numbers give you longer wavelengths. And it's always an oscillatory function because you have an exponent. In an exponent, you have an iota term. And an exponent of an iota term gives you cosine and sine functions. So whenever you have exponent iota times a real number or minus iota times a real number, you have an oscillatory function. So this is a solution of the Schrodinger equation. And you can find the coefficients. Now let me give you an example. Suppose you have an atom. This is Earth. And you have an atom of cesium. Cesium is an element. You trap the cesium atom. Now it falls under the action of gravity. So these kinds of experiments are routinely performed and they are called atomic fountain experiments. Now this cesium atom has an energy E. It is trapped inside a magneto-optical trap. You shine laser light on it and the atom is trapped at a certain height above the ground. You switch off the laser and what happens is this atom falls down to earth in the form of water falling down a fountain. Now what I would like you to do for this particular case, I would like you to estimate, using the concepts that we've learned so far, what the wave function of this falling atom would look like. The energy is fixed, and as it comes down, the potential energy of the system is changing. I would like you to estimate what the wave function of this falling atom will look like. I give you 3-4 minutes to think about it. क्वेश्चन समझ आया? पोटेंशियल एनर्जी देखो कैसे वेरी हो रही है.
पहले फंक्शन निकालो कि ax plus b टाइप का फंक्शन आ जाएगा.
I don't want you to give me a mathematical form of the solution, just draw the wave function. What will it look like? ठीक है, शाबाश. ये हाइट अबव ग्राउंड यू इस तरह उसको एरो बना लो. हाइट इस तरफ. डैम्पिंग नहीं होगी, एनर्जी तो कांस्टेंट है ना. हाइट अबव ग्राउंड किस तरफ है? हाइट डिक्रीज होगी इस तरफ बच्चों. शाबाश. So this is a plot of the potential energy versus height. You increase the height, the potential energy goes up. This means that at higher levels the potential energy is high, therefore E minus U is small. When E minus U is small, then the wave number is small. Wave number small means the wavelength is longer. The wavelength is longer at the beginning, and then it starts So this is an approximate form of the wave function of this falling atom. And again, do not fall into the trap of thinking that the atom is in motion. It's falling down from a certain height to the ground. Think that when you're not making a measurement, there's a wave function associated with this falling atom, and the wave function is spread over the entire height, that is from its initial trap to the earth. So this is the wave function of this falling atom. So in the homework that I've given you, there's another question that talks about all kinds of strange potential energy functions. For example, here we're talking about a square potential well. What if this potential well is a triangular well, like this? And you have an energy which is always greater than the potential energy. In fact, these wells are formed in semiconductor electronic circuits. Whenever you make a junction between a p-type material and an n-type material, these wells are formed. And they have all kinds of shapes. Trapezoidal shapes, triangular shapes, parabolic shapes. Therefore, if you want to become good electrical engineers with a sound understanding of device physics, you really need to understand this stuff in somewhat detail. Now, I would like to move on to a very counterintuitive application of trapping electrons inside wells. Everything looks rosy and cozy so far because the energy of the electron is greater than the potential energy. The system is unbound and the kinetic energy is positive. Now let's consider a situation in which we have a finite well x equals 0, x equals L, height u0, but we come up with a very interesting situation in which the energy of the system, energy of the electron is E. Inside the well, it is greater than the potential energy, but outside the well, it is smaller than the potential energy. Now, is this a bound or an unbound system? It's a bound system. Classically so. Classical physics tells us that since at these turning points A and B, beyond these points, the energy is smaller than the potential energy, therefore, the wave function cannot extend in these classically forbidden regions. This is classically forbidden, this is classically forbidden. ठीक है, ये एक शजरे ममनू है इलेक्ट्रॉन के लिए, एक ऐसा दरख्त है जिसका फल उसको खाने की इजाजत नहीं है, लेकिन ये क्लासिकल फिजिक्स है, याद रखें. अब देखते हैं क्या क्वांटम फिजिक्स हमारे लिए कोई और इंटरेस्टिंग सिनेरियोज लेके आता है या नहीं. और कल परसों आपने मुझे बताया था कि व्हेन वी टॉक अबाउट नेगेटिव काइनेटिक एनर्जीज, इट्स नॉनसेंस. नेगेटिव काइनेटिक एनर्जी हो ही नहीं सकती. ठीक है, तो क्या देखते हैं कि वेदर दिस होल्ड्स ट्रू इन द क्वांटम वर्ल्ड और नॉट. What is our guiding light? What is our beacon of hope? It's the Schrodinger equation. The Schrodinger equation defines what the wave function should be. So inside the well, everything remains the same. The wave function is simply given by, the wave number is simply given by this, and this is the wave function. So in this region, inside the well, in region number 2, the wave function is exponent iota, let's call it k2, x plus exponent minus iota k2x. Now what is k2? k2 क्या है? वेव नंबर है, इसका स्क्वायर है 2m e minus u0 which is 0. यहाँ पे 0 है ना पोटेंशियल एनर्जी, 2me over h bar squared. So this is an oscillatory function. This is a real number, k2 is a real number, and you have an exponent of iota times a real number. So you have an oscillatory function here. So what you expect in this region, without going into too much detail, you expect that the wave function inside the well will be oscillatory. Now if this were an infinite well, we've already shown that the wave function at these boundaries should go to 0. The wave function at the boundaries should go to 0, and it should be 0 in the classically forbidden region as well as in this forbidden region. But now it's not an infinite well. The barrier is not infinite, it's finite. Classically the barrier is still unsurmountable. समझते हैं बात? Classically the particle does not have enough energy to surmount or to overcome the obstacle presented by the potential energy. So classically we should not let the particle go into the classically forbidden region. But what is happening quantum mechanically? Okay, we have no other choice but to look at the Schrodinger equation again and solve the Schrodinger equation. So if we solve the Schrodinger equation, say for region number 1, what is the Schrodinger equation? It's given over there. This is the characteristic equation. So let's write the characteristic equation again. The characteristic equation is p squared equals minus 2m h bar squared E minus u naught. Now which one of these is greater? U naught is greater. So this is negative. A negative with a negative becomes positive. So I can write this to be alpha squared, where alpha is positive, and alpha squared is defined as 2m over h bar squared u naught minus e. It's a positive number. Alpha squared means that it's always a positive number because the square of anything is a positive number. So p square is now a positive number. Previously in this case p squared is a negative number. Therefore our solutions had an iota in the exponent, because when we take the square root you get an iota term here. But this scenario is different now. P square is now a positive term, which means that the roots p, which are p1 and p2, they are plus alpha and minus alpha, and they are real numbers. So when we write the solution for the Schrodinger equation in region number 1, we have some a, याद रखें यहाँ c और d भी हैं कोई इस वाले केस में. Okay, in region 1 we have a exponent alpha x. There is no iota here. There is no iota here. Alpha is a real number, plus b exponent minus alpha x. So this is the solution for x is smaller than 0. Let's write all the solutions together. In region number 2, which is the well, our solution is c exponent iota k 2x plus d exponent minus iota k 2x. This is for x inside the well. And for x greater than L, could anyone tell me what the solution is? You didn't get what? The first, this thing? ये वाला? देखिए, E is smaller than U naught, which means U naught is greater than E. So this thing, what I've written in parentheses is negative, but there's a negative sign here as well. So all of the right hand side is positive. It's a positive number. I, out of my free will, which I have been given, being a citizen of Pakistan, I can call this alpha squared. ठीक है? I can call this alpha squared. Alpha squared is always positive. So I just call it alpha squared. I can call it alpha anything. I call it alpha squared. Now p squared are the roots of the characteristic equation. They are equal to alpha squared. The roots are plus alpha and minus alpha. So my solution is exponent of one of the roots, which is alpha x, plus b times exponent the other root, which is minus alpha x. So this is the solution of the equation. There is no iota here. Like in the second, in the well, there is an iota. What about the wave function in region number 3? नहीं, मैं आयोटा आ ही नहीं रहा ना, कॉम्प्लेक्स नंबर आ ही नहीं रहा, मैंने अवॉइड नहीं किया. नेगेटिव है ही नहीं ना, ये मैंने अवॉइड नहीं किया, नेचर ने आपको सहूलत दी है. ठीक है कि ये रियल पॉजिटिव नंबर आ रहा है. अच्छा, व्हाट्स द सॉल्यूशन, व्हाट्स द वेव फंक्शन इन रीजन 3? इट्स लाइक 1, similar to 1, but different coefficients. Remember, the coefficients have to be different. So I can write E exponent alpha x plus D exponent minus alpha x. This is for all right. Alright, now let's use certain properties of the wave function. Again, the last 15 minutes are very important because we are inching closer to the destination. Now, let's use certain properties of the wave function. One property of the wave function is that the wave function can never go to infinity. Because if the wave function were to go to infinity, that will lead to an unphysical situation. Why? Why can't the wavelength zero नहीं होगी? Wave function क्यों नहीं infinity जा रहा? Continuity की आप वजह बता रहे हैं, लेकिन wave function क्यों नहीं infinite हो सकता? क्योंकि probabilities को finite रखना होता है. वेव फंक्शन का मॉडुलस स्क्वायर तो प्रोबेबिलिटी को जाहिर करता है, तो वेव फंक्शन कैन नेवर गो टू इंफिनिटी. इफ यू लुक एट नंबर 3, सॉल्यूशन नंबर 3, अल्फा इज पॉजिटिव. इफ x goes to infinity, which of these terms blows out? Which of these terms diverges? The first one. So this term, this e should be 0. This is 0. देखो, हमने मैथमेटिक्स ने अब ये वाक्य है, अब मैथमेटिक्स ना आपको एक खास मकाम तक लेके जाती है, ठीक है, उसके आगे चल के ना मैथमेटिक्स के पर जल जाते हैं, वो उधर तक ही जाती है. मैथमेटिक्स आपको ये सारे सॉल्यूशन देती है, आगे आपने फिजिक्स के घोड़े पे बैठ के जाना है. अब फिजिक्स आपको ये कहती है कि भाई ये वाला सॉल्यूशन डाइवर्ज कर रहा है अगर x इंफिनिटी जा रहा है, तो दिस कोएफिशिएंट हैज टू बी 0. ठीक है, therefore mathematicians alone cannot do physics. So this coefficient is 0. We know this. All right, we have simplified the solution a little bit. What about the wave function in region 1? Which of these terms is diverging when x goes to minus infinity? This. So b has to be 0. So we have simplified the solutions a little bit. So now let's apply the boundary conditions at x equals 0. At x equals 0, these wave functions must be equal. Right? Because the wave function has to be continuous, which means that a has to be equal to c plus d. क्योंकि अगर आप 0 डालें इसके अंदर तो ये 1 हो जाता है, ये 1 हो जाता है, ये 1 होता है, तो a has to be equal to c plus d. The other condition that has to be implemented on x equals 0 is that the derivative of the two wave functions must be equal at the x equals 0 point. So you have alpha a equals iota k2 c minus d. So these are two conditions, and there have two conditions at x equals L. At x equals L, we have c exponent iota k2 L plus d exponent minus iota k2 L must equal f exponent minus alpha L. And if we apply the continuity of the first derivatives, we have iota k2 exponent c exponent iota k2 L plus exponent minus iota k2 L equals minus alpha f exponent minus iota minus alpha L. So these are the four boundary conditions. You should be able to write these conditions on your own in the midterm or in any assignment or in any quiz. You should be at least be able to write down the boundary conditions, and in some cases I may ask you to solve these as well. But so you can go home and solve what these boundary conditions are. You can solve the value of A, C, D, F and so on. But the important point I would like to emphasize here is the following. Let's consider region number 3. Can you hear me? Look at the wave function in region number 3. It's s exponent minus alpha x. What is the wave function equal to at x equals L? Is it 0? If you put x equals to L here, is the wave function 0? No, it's only 0 if f were 0, but f is not 0. Likewise in region number 1, this is your wave function. Is the wave function 0 at x equals 0? It's 0 only if a is 0, but that's not the case. The wave function at the boundaries has not gone down to 0. If you look at region number 3 and if you would like to plot this wave function with respect to x, what would this look like? It's an exponential decay. And what is the wave function in region 1? It's an exponential decay as well. X negative है याद रहे. It's an exponential decay as well. So now what have we achieved? Is there anything strange about this? इसमें कोई अनहोनी बात, कोई अछूती बात, कोई हैरानकुन बात नजर आ रही है आपको? हाँ बिल्कुल है. और वो क्या है? वो ये है कि even though classically the electron classically the electron does not have enough energy to cross this barrier because the energy is smaller than the potential energy. Yet by solving the Schrodinger equation, which actually you should go home and solve these coefficients. When you solve these coefficients, you will have further confidence in what I am saying. And what I am saying really is that the wave function does not go to 0 at the boundary, and it's not 0 throughout the region, the classically forbidden region. The wave function in fact has a finite amplitude and it rapidly decays to 0, but it penetrates into the classically forbidden region. Likewise, in this classically forbidden region, the wave function penetrates over a certain length. So there is penetration of the wave function. So let me draw another diagram that describes this. So inside the well, where the energy is greater than the potential energy, the wave function is oscillatory. And it has a certain wavelength and a certain wave number. And that wave number squared, k squared, is given by 2m e minus u, which is 0, over h bar squared. So we have an oscillatory wave function inside the well because the energy is greater than the potential energy. This is a classically allowed region, but these regions are classically forbidden. But by solving the Schrodinger equation, we get this revealing fact prized open to us, that the wave function does not disappear to 0. The wave function penetrates into the classically forbidden region over a certain length before it goes to a very small number. It never goes to really 0, but it goes to imperceptibly small numbers. An exponential never decays to 0, but for practical purposes it goes very close to 0. Likewise, in this region, the wave function penetrates into the classically forbidden region. And this is something that is classically totally nonsense. A system does not have enough energy to surmount a barrier, yet there are instances when the particle can surmount the barrier even though it doesn't have sufficient energy and go into a classically forbidden region. So this is the prelude to what is called tunneling. That is, a particle can access classically forbidden regions. Or in other words, in the quantum world, there is no inaccessible region for a particle. Every region is accessible. So this leakage of the wave function into the classically forbidden region happens over a certain length scale, delta, which is called the penetration length. And if you look at the function, the form of the wave function, it's exponent minus alpha x. So the penetration length is defined as the length over which the wave function drops to 1 over e of its value. So this delta is really 1 over alpha, which is h bar 2m u naught minus e. So this could be in nanometers, this could be in picometers, this could be in centimeters, this could be generally a very small number because h bar is extremely small. And larger the difference between u naught and e, smaller will be the penetration length. Smaller is the difference between u naught and e, larger will be the penetration length. So I will give you some numerical examples to find out what the penetration length of the wave function is. Now the last thing I would like to mention is, in this particular case, when the wave function has gone into the classically forbidden region, is there negative kinetic energy here? Classically, this is a very stupid question to ask, because kinetic energy can never be negative. But quantum mechanically, the energy here indeed is a negative kinetic energy, because the potential energy is greater than the total energy. So kinetic energy has to be negative. The question is, in real experiments, do you find, since the wave function is finite, if you take the modulus squared of this wave function, there is a finite probability of detecting the electron in this classically forbidden region, and there is a finite probability of detecting the electron in this classically forbidden region. So can we perform an experiment that detects the electron to exist in this classically forbidden region? Now I would like you to think about this over the next 2 days, and I would like you to take the support of uncertainty principle. And I would like you to think is that if the uncertainty in the length delta x is of the order of the penetration length, what should be the momentum of this particle and what should be the energy of this particle? What should be the uncertainty in the energy? And if you are able to detect the particle inside this region. So now we've learned a very strange thing today. And what we've learned is that there are regions which are classically forbidden for particles. But when you enter the quantum realm, of all the strangeness and quirkiness that quantum physics tells us, there's another quirkiness that it adds. And that quirkiness is the fact that a particle can access inaccessible regions which are classically inaccessible. Let me finish by one example. And we'll talk about tunneling. Just 1 minute, please. An example from optics. अच्छा ये देखें, there is a light ray from glass entering into air. Suppose this angle of incidence is greater than the critical angle. What will happen? Total internal reflection happens. All the light goes back in, and none of the light is transmitted. Okay. Now there is another glass slab that is placed near to this glass, and there is a wedge of air in between. Now suppose the ray of light is incident here. It's all reflected. Fine. The ray of light is incident here. It's all reflected. Fine. Because the angle is greater than the critical angle. But here what you observe, when this thickness is very small, when this thickness of air is extremely small, what you observe is that all of the light is not reflected. Some of the light has leaked into the barrier, which is air, and is transmitted into the other medium. So that this phenomenon is a classical analog of tunneling, and is called optical tunneling. So the requirement for this tunneling is that this thickness which intervenes the two glass materials has to be extremely small, smaller than the wavelength of light perhaps. So when this condition is satisfied, all of the light is not reflected and the total internal reflection is what is called frustrated. So this is an example of frustrated total internal reflection. That is, total internal reflection does not happen totally. Some of the light is leaking into the other medium in the form of what are called evanescent waves. So this is an optical analog of quantum mechanical tunneling. In our next lecture, we'll look at tunneling in a bit more detail and study some of its applications.